Today we are going to begin talking a lot more formally about light. Light is another wave. It is a three-dimensional wave like sound is, but it's a little bit different because what do we know about light so far? We know that light is sort of a catch-all phrase for all forms of electromagnetic waves, right? And so we know that all light is an electromagnetic wave. What else do we know about light? That it is a transverse wave, meaning that there's something vibrating perpendicular to the direction of energy transfer, and we'll talk about that as time goes on. Now, what do these two things mean? Let's just recall the fact that it's an electromagnetic wave. What's our test? That's right, these can travel through a vacuum. Okay, I know that's not real English there, but there you go. Transverse, what does that mean? Right, that means that these can be polarized, and we'll come back to that later. So we know we have two tests to prove that light is electromagnetic because it can travel through a vacuum and it can be polarized. So let's talk about some other basic information about light before we get into the meat of today. The first thing is the speed of light. So truly important phrase. All frequencies of light travel at the same speed in a vacuum. Okay? Super important. It's a fundamental law of nature, no matter who you're talking to. So this is really important. So we should talk about what that speed is. First is that speed is ridiculously quick. And second, the speed of light in a vacuum comes up so often, we actually give it its own variable, c, lowercase c, and that's the speed of light in a vacuum. So how fast is that? Well, that's 3 times 10 to the 8th meters per second. Actually, we could even go to 3 sig figs and it's still 3.00 times 10 to the 8th meters per second. We could go out to many more significant figures. We have experimentally determined this speed out to about 16 or 17 significant figures in case, depending on the precision that your experiment needs. But for our purposes, we'll be using this value. How fast is that? Just to give you a flavor, from here to California is about 300 miles. 300 miles is roughly about 4,800 kilometers. So if we're thinking how long would it take light to travel to California from New York? So if the distance here is 4,800 kilometers, well, we want to make sure our units match. So it's 4.8 times 10 to the 3rd kilometers, which is 4.8 times 10 to the 6th meters, or 4.8 megameters, 4.8 million meters. How long does that take? Well, time is going to be distance over the average speed. And so that would be 4.8 times 10 to the 6 meters divided by 3 times 10 to the 8th meters per second. We throw that into our calculator and let's see what we get. 4.6 E6, 3 E8. We're going to be using a lot of really, really big numbers and really, really, really small numbers in this unit. So we got to get used to our conversions again between kilometers and megameters and giga and micro and nano and all sorts of good stuff. So just be aware of that. But this is 0.0153 seconds. So barely less than 2/100ths of a second to go from New York to California, which is just insanely, incomprehensibly fast. So that's an important thing to say. Now, the next thing, kind of a corollary to that, in all other media, light travels slower. Okay? Now, in another lesson, we'll talk about how much slower and a way of calculating that, but it's important to note that once light goes into any other medium other than vacuum, it travels slower, meaning that this number is sometimes considered a universal speed limit because nothing can travel faster than the speed of light in a vacuum. Well, nothing Nothing that we know about that exists in the universe as we know it travels faster than the speed of light in a vacuum. Let me be super precise about that. So there you go, some basic facts. Now, some other vocabulary words that I want to talk about. Let's talk about the mechanism of seeing. So why do you see this pen here? Well, what happens for you to see this pen, light has to get from the pen to your eye to signal, and if we want to be really specific about it, the retina of your eye, in order for you to be able to see this. But where does that light come from? So if I was in a perfectly dark room, we wouldn't see the pen. It would still be there, but we wouldn't see it. Why? Because there needs to be some sort of source of light that shines light off of this. When the light shines off of this, it then is transformed in a particular way, and we'll talk about that in the next video. And then once it's transformed, the transformed light gets to our eye. So the important thing here is the mechanism of seeing requires light to get from the object to our eye. Right? If it doesn't get to our eye, we don't see it. If there's no light, we don't see it. Okay? A couple of things about that. How does that normally happen? So a source of light sends out light. It hits the object. The object transforms the light. We'll talk about how and what that means. And then the transformed light gets to our retina. If any of those steps fail, we don't see the object. So just keep that in mind, the mechanism of seeing. Something else about the mechanism of seeing, our brain has evolved to do something really specific with this. How does our brain believe that light travels? Well, the correct answer here is the brain believes light travels in straight lines. And actually, light tends to travel in straight lines unless it has been transformed in some way, shape, or form or affected by other things. Hopefully, that's starting to think about the properties of waves. Those are going to be some of the ways that light can be transformed, right? And change its direction, but absent those things happening like reflection, refraction, and diffraction, light is going to travel in straight lines, so it's perfectly reasonable from an evolutionary standpoint for our brain to believe that or perceive things in that way. Okay, some other vocabulary. So we were talking here before about sources of light. Well, all objects can be divided up into two groups, and those two groups are objects can either be luminous or illuminated. Luminous, excuse me. Luminous or illuminated. So what do you think those words mean? All right, well, hopefully what you're thinking about is here, I've got my flashlight. The bulb of my flashlight, when lit, and I'm not going to shine it into the camera because that's rude, would be luminous. The light bulb is a source of its own light, whereas I guess this itself is not a source of its own light. You're seeing this because it's reflecting light. Okay? And so that's the difference. Luminous object is a source of light. Illuminated objects reflect light. And so the classic examples of these, what do you think? Hopefully you said the sun and the moon, and there you go, luminous versus illuminated. All right, a couple of other words that we want to talk about regarding light. You probably have heard these words before. We're going to have transparent, translucent, and the third of the triumvirate there, opaque. Transparent, translucent, and opaque. So I'm going to stop the video for a second and think to yourself, what are some objects that you think are transparent, translucent, and opaque? All right, here we go. Hopefully transparent, you said things like water or a drinking glass is transparent. Hopefully for translucent, you think like, like this frosted plastic or a tinted car window or stained glass would be examples of translucent. Wet paper is translucent as well. Opaque, this wood table, this paper, my hand is opaque. So what does it mean for things to be transparent, translucent, and opaque? Well, so let's just define them. A transparent object is an object that allows for the transmission of visible light through it with minimal distortion. Right? I'm not going to pretend that it's perfectly, there's no distortion, but with minimal distortion, such that we can see images clearly through it. Okay? A translucent object is an object that does not allow for the easy transmission. Rather, it causes significant distortion, okay, of the light. So say, for example, this frosted thing, you could probably see that my hand is below the picture, but you can't see exactly the image of my hand. With stained glass, you can see the shape of shadows of objects, but you can't see the objects themselves. With like a tinted glass, you can kind of see like a ghostly outline of the image, but you can't see the object clearly. So you can't see objects clearly through them. All right, and then opaque is an object that blocks the transmission of visible light. Okay, so clear difference there. Notice in these three definitions, I'm saying visible light, because we're going to see that when we start talking about other forms of electromagnetic radiation, that an object that is opaque, meaning doesn't allow for the transmission of visible light, might let other types of electromagnetic radiation through it. But when we use these three words, we are generally talking with reference to the visible portion of the spectrum of light. So luminous versus illuminated, transparent, translucent, opaque. Some just basic vocabulary about light. Now, next, other words with light. In sound, when I said frequency, we knew that there was a word that meant frequency of sound, and that word is, hopefully you said to yourself, pitch. When we're talking about the frequency of light, the word that describes the frequency of light is color, right? So a color of light talks about a frequency of light. Now, hopefully, at the end of this, we'll have expanded your definition of what color means, because color just means a certain part of the electromagnetic spectrum. When we're talking about the amplitude of the light, we don't say, hey, what's the amplitude of the light? Turn up the amplitude of the light. You may say a slightly more scientific term, the intensity of the light, and that's how scientists will most often talk. But then when we get to colloquial words, what hopefully you're thinking here is the notion of brightness. So brightness has to do with the amplitude of light. Frequency has to do with the color of light. Okay? So if we're increasing the brightness of light, really what you're doing is increasing the amplitude of the wave. It gets a little complicated there. Now, technically, there is a unit for the brightness of light. You may have heard it before. It is something called a lumen. but like honestly couldn't tell you all that much about the concept of lumens. They don't often come up. There's another one out there. It's something called the candela, because light used to be measured back when we first started measuring the brightness of light in terms of candle power. Like how many candles would you need in order to have that brightness of light? And that's where the candela came from. The candela became the lumen once we got a little bit better with our knowledge of light as an electromagnetic wave. But there we go. Now, what I really wanted to talk about today is the electromagnetic spectrum. So I want to put the electromagnetic spectrum in order, but we need an ordering principle to do that. Okay, so what would be a way of dealing with the electromagnetic spectrum? Well, there's two sort of ways we can think of. A lot of people are in chemistry, you probably learned the electromagnetic spectrum as sorted by wavelength, right? But we're not going to do that here. Why would we not want to sort the electromagnetic spectrum by wavelength? Well, the question here becomes, what affects wavelength? If you remember, using the wave equation, V is equal to F lambda, or more properly, lambda is equal to V over F, that a given wave can change its lambda not only by changing the frequency of the wave, but by changing the medium that's in it, that it's in. But if you take a an object here, so here's my glass of water, and I take, you can see the red portion of my pen. Actually, let me just do this. The red cap of my pen. If I put that in there, it still looks red to us, right? Therefore, we don't want to do something that's based on a property or a description that can change, since it obviously doesn't change depending on the medium that it's in. Therefore, when we're talking about an ordering principle for the electromagnetic spectrum, we want to organize it by frequency then, because frequency doesn't change based on medium. So we're going to order this from high frequency to low frequency. Now, before we get into this, how are we going to know how to do this? What's a good question? What we're going to do here is by frequency is going to mean something very specific here. I want you to recall the definition of the term amplitude. Okay? So, amplitude. What does amplitude mean? Well, amplitude, remember, was the energy transported, and then there was a really important phrase, per cycle by a wave. Okay? Per cycle. So a high amplitude wave would transport more energy per cycle. But I want you also to think about what frequency is. Frequency is the number of waves created per unit time. That means, say, in 1 second, a higher frequency wave will transmit more individual waves to something than something with a low frequency, which means that a higher frequency wave will transmit more energy per second than a low frequency wave if those two waves have the same amplitude. Because this only talks about the energy per cycle. Frequency then, if we talk about energy transmitted, a very important fact is that the energy transmitted by light is directly proportional to the frequency of light. Because frequency, right, or really what I'm saying here is that higher frequency waves transmit more energy in a given amount of time than low frequency waves, assuming equal amplitude. Okay? And therefore, the way we can do this is we can think, well, if higher frequency waves transmit more energy in the same amount of time as low frequency waves, that's going to mean that high frequency waves are going to be more dangerous because they transmit more energy in the same amount of time. So I'm going to stop this video now because it's getting kind of long, and the next video is going to talk about ordering the electromagnetic spectrum in terms of from least dangerous to most dangerous. So what I want you to think about for now is, what do you think are the least most dangerous waves to the most dangerous waves? And we'll talk about that in the next video.